Hello everyone, this is Sarita from GDCW Begumpet. I welcome you all to the another session of IR spectroscopy. We have completed part 1 in this. So in part 1 we have seen the introduction part of IR spectroscopy, where we have seen the principle and the different types of molecular vibrations. And we have also seen how to calculate the number of vibrational modes for linear and non-linear molecules. So today we'll continue with the vibrational frequencies. We have also seen the Hooke's law, how the vibrational frequency changes with the force constant as well as the mass of the atoms. So in the formula, that is nu bar is equal to 1 by 2 pi under root k by mu, where k is the force constant and mu is the reduced mass. So as the force constant increases, vibrational frequency also increases. And vibrational frequency is inversely proportional to the mass. So as the mass increases, the vibrational frequency decreases. So we'll continue with the next topic in that is the factors affecting the vibrational frequency. So what are the factors that affect vibrational frequency are? We have 4 factors here: coupling interaction, Fermi resonance, hydrogen bonding, electronic displacement effects. So first factor is coupling interactions. So here you can see it is a CH2 group, that is methylene group. So here a stretching absorption frequency for an isolated CH bond we have to expect. But in the case of methylene, we will observe 2 absorption bands. So that is due to the coupling interactions between the CH2 groups. So those 2 bands are formed by symmetric stretching and asymmetric stretching. So we have seen stretching vibrations will change the bond length. So here you can see this is symmetric stretching, where both the hydrogens are moving apart from the carbon. Whereas asymmetric stretching, one hydrogen we are compressing it and the other hydrogen we are pulling apart. So because of these 2 asymmetric and symmetric stretchings, we will observe 2 bands for CH2 group. So this is about the coupled vibrations. So and always asymmetric vibrations appear at higher wavelength when compared to the symmetric vibrations. The second factor is Fermi resonance. So this Fermi resonance, it occurs when a fundamental vibration couples with an overtone or combination bands. So first we need to know what is fundamental and then the overtone and the combined bands. So fundamental transitions are those where the transitions taking place from V0 to V1. So when the molecule absorbs IR radiation, so the transitions takes place in the vibrational energy levels, as we have seen in our last class. So in those vibrational energy levels, it consists of rotational energy levels also. So because of these transitions, IR spectra is also known as vibrational and rotational spectroscopy. So here, when it is absorbing the radiations, IR radiations, so you can see the transitions from V0, that is ground state vibrational energy level, it is getting excited to the first excited vibrational energy level, that is V1. So from V0 to V1, if the transition is taking place, those transitions we call it as fundamental transitions. And these fundamental transitions are unique for each and every that is the functional group present in the compound. Then there is another type of transition which we call them as overtones. Suppose sometimes what happens is the transition takes place from V0 to V2. From V0, that is from this V0 to V2. So then that we call it as overtone. So we have first overtone, second overtone also. So when it is taking place from V0 to V2, it is known as first overtone. So where the difference in the energy will be equal to 1. Then there are combination bands. Combination bands occur because of when 2 fundamental frequencies, when they combine and they are excited simultaneously. So if these two fundamental vibrations, when they combine, it will give rise to a combination band. So we have fundamental bands or overtones and combination bands in IR. So what is Fermi resonance now? Now Fermi resonance, it occurs when fundamental vibration. So this is fundamental transition which is taking place when this is coupling with the overtone bands or the combination bands. So when an overtone or combination bands has the same frequency to that of the fundamental, two bands appear close together. So these are the two bands which appear very close to each other as a doublet, and they are because of Fermi resonance. So Fermi resonance is nothing but the bands which appear due to the frequencies of overtone bands when it is equal to the fundamental bands. Now suppose if we take an example of any aldehyde, C double bond O H. So in this aldehydes, Fermi resonant bands appear. The overtone of CH deformation mode appears at 1400 and is always in Fermi resonance with the stretch of the same band, that is CH stretching band, at 2800 centimeter inverse. So for aldehyde, we find a doublet at 2800 centimeter inverse. So that is nothing but it is forming due to this Fermi resonance. So Fermi resonance bands are nothing but they are formed because of the overtones or combination bands having same frequency to that of the fundamental bands. So when the bands frequencies are same, then these Fermi resonance bands appear, and always they appear as a doublet. That is two bands appearing very close to each other. Then if we take another example of carbon dioxide. So carbon dioxide, it is a triatomic molecule. It consists of two C double bond O bonds. So in this way. Now, even in this, we have to see the Fermi resonance. So two fundamental stretching vibrations appear even in this case, that is symmetric and asymmetric. So symmetric stretching vibrations produces no change in the dipole moment because the carbon double bond oxygen, and here also it is carbon double bond oxygen. So in symmetrical stretching, what happens, because these two are oxygens only, that means if you stretch them or if we compress them in symmetric stretching, there won't be any change in the dipole moment. So that is the reason why symmetric stretching is IR inactive of carbon dioxide. So we don't find that vibrational frequency for carbon dioxide. Whereas in asymmetric vibration, one oxygen approaches the carbon and the other moves away. So that asymmetric stretching vibration, it appears in the region 2330. Third factor is hydrogen bonding. So hydrogen bonding also changes the vibrational frequency values. So here, when hydrogen bonding is formed, what happens is the frequency shifts towards the lower wave number. Why it shifts towards the lower wave number is, so as we know that when a hydrogen bond is formed, so the bond length will increase, and when the bond length increases, the force constant will decrease. So as we know that the vibrational frequency is directly proportional to the bond strength or the force constant. So when the force constant decreases, vibrational frequency also decreases. So that is the reason why when a hydrogen bonding is formed, the vibrational frequency will move towards the lower wave number. And in this, we have two types of hydrogen bonds. Those are intermolecular hydrogen bonds and the other is intramolecular hydrogen bonds. So intermolecular hydrogen bonding means the hydrogen bond formed between two atoms, two different molecules. Whereas intramolecular hydrogen bond is the hydrogen bond which is formed within the molecule. So how to differentiate between these two. That we can do by this IR study. So intermolecular hydrogen bonds are concentration dependent. So remember this point, intermolecular hydrogen bonds are concentration dependent. So as you change the concentration, the intermolecular hydrogen bond also changes. That is, the frequency value will change. Suppose on dilution, the intensities of such bands decreases and it finally disappears also. So on dilution, if the change in the vibrational frequency is taking place, then that particular molecule is having intermolecular hydrogen bond. Suppose if on dilution, if there is no change in the vibrational frequency, then we can say that that particular molecule is showing intramolecular hydrogen bonding. So we'll see with an example here. This is para-hydroxymethyl-benzoate. This is para-hydroxymethyl-benzoate. Now these are the two molecules of para-hydroxymethyl-benzoate where they are participating in intermolecular hydrogen bonding. And this is the another isomer of that where OH group is ortho. So this is ortho isomer. So ortho-hydroxymethyl-benzoate, which is showing intramolecular hydrogen bonding. You can see the hydrogen bonding is formed within the molecule there. Now, in such cases, there is one more difference where intermolecular hydrogen bondings will show broad bands, whereas intramolecular will show sharp bands. So because of this intermolecular hydrogen bonding, the band will be a little bit broad, whereas for intra it is sharp. So what is happening when this hydrogen bonding is formed? This OH stretching vibrations, the bond length of this OH will increase because this hydrogen oxygen is attracting this hydrogen towards itself. So what will happen is this bond length will get increased, or we can say that the force constant of this bond will decrease. So when it decreases, force constant decreases, vibrational frequency also decreases. So that is the reason why the hydrogen bondings, when it is present in any molecule, it will show a frequency less. So here it is showing at 1680 centimeter inverse. Then you can see another example of carboxylic acids. So the hydrogen bondings generally we see in alcohols, carboxylic acids, amines, etc. They are all affected by this hydrogen bondings. So the carboxylic acid in the gaseous phase. Okay, in the gaseous phase, you can see the narrow OH stretching vibration. Whereas when it is in the form of a dimer, so we can see the intermolecular hydrogen bondings between the two molecules of carboxylic acids. This is a dimer. So it is intermolecular hydrogen bonding. So you will get a broad OH stretching vibration in this way. So intermolecular will give broad band, whereas intramolecular will give narrow OH stretching bands. Then the other that is effect is electronic displacement effect. Now this electronic effects can also change the absorption frequencies. So what are those electronic effects are? Inductive effect, mesomeric effect, configuration effect, or it is field effect. So what happens under all these effects? The force constant will change. So when the force constant or the bond strength changes, its absorption frequency also changes, because absorption frequency is directly proportional to the force constant. Suppose if we take an example of any alkyl group. Suppose an alkyl group is introduced in the alpha position of carbonyl group. What happens? So it exerts some inductive effect, which results in shortening or strengthening of the bond. So because it is giving electrons, so what happens is the electrons are flowing towards the carbon, this carbonyl group, and this C double bond O, the bond length will decrease. So when bond length decreases, high amount of energy is required to break the bond. That is, the force constant is more. So when the force constant is increasing, the frequency or the absorption frequency also increases. So that is in the case of the alkyl group, which is acting as the plus I group. That is, it is releasing the electrons. So as we know that inductive effects are of two types. One is positive inductive effect, which is plus I, we call it as, and negative inductive effect, it is minus I. So for example, if we are taking same alkyl group, so what is happening? Bond length is increasing. So K value is decreasing. Frequency also decreases. So here you have to note one point. Here bond length is decreasing. This is where chlorine, bromine, iodine we are taking. They are acting as minus I group. So they will, that is, attract the electrons towards itself. So C double bond O bond length will decrease. So when bond length is decreasing, K value will increase and the frequency also increases. Whereas in the case of alkyl group, as it is giving the electrons to C double bond O, there the bond length will increase. So K value will decrease, frequency also decreases. So you can see in an example here, acetone. Acetone shows C double bond O stretching vibrations at 1715 centimeter inverse. Whereas another example, chloroacetone. So where we are having chlorine at the alpha position, it is showing increase in the C double bond O stretching vibrations. Why it is showing increase is this chlorine, when it is attached at the alpha position, as it is a minus I group, it withdraws the electrons from the C double bond O group. That means the C double bond O group bond length will decrease. So when the C double bond O bond length decreases, its force constant increases. So force constant, as it is directly proportional to the frequency, frequency also increases. Then we also have another effect, that is mesomeric effect, where here we are taking an example of acetophenone and para-amino acetophenone. So acetophenone is CH3, CO and a benzene ring attached to that. So there acetophenone shows a C double bond of frequency at 1693 centimeter inverse. Whereas para-amino acetophenone is showing 1677. Now what is the reason here is amino group is having electrons, lone pair of electrons. So those lone pair of electrons can be delocalized into the benzene ring and then towards the C double bond O group also. So that means what is happening to the bond length? Bond length will increase. So bond length increases, K value decreases, so frequency also decreases. So that is the reason when we have amino group, the bond length will decrease, bond length increases and frequency is decreasing. Then if we take an example of amide and ester. So here we have taken example of benzamide and the other ester, that is phenyl acetate. So phenyl acetate will show higher vibrational frequency, that is 1730, whereas benzamide is showing 1663. So why benzamide is showing lesser vibrational frequency is again due to the same factor. Suppose if we are taking an amide, so nitrogen lone pair electrons are delocalized in this way. So what happens to C double bond O? It becomes C single bond O. So C single bond O means bond length is increasing. Therefore, the K value decreases and the vibrational frequency also decreases. So these are the different functional groups we are showing. One is acid chlorides, anhydrides, esters, amides. So acid chlorides, where chlorine is attached here at the carbonyl group, and it is showing minus I effect. So minus I effect dominates in this case. So when minus I effect is there, this C double bond O will come closer. That is the bond C double bond O bond length will decrease. So when the C double bond O bond length decreases, the vibrational frequency will increase. So that is why it is showing at a higher vibrational frequency, which is 18-15 centimeter inverse. Then anhydrides. Anhydrides, here we have a tug of war for lone pair electrons. See here, the lone pair electrons are present on the center oxygen, where it can be delocalized onto this carbonyl group or else the other carbonyl group. Now what happens in such cases? So here also inductive effect is dominating. So two peaks appear at 1790 and 1810 centimeter inverse. Whereas esters will show lesser this value, absorption value, because OH which is there, the oxygen again having lone pair electrons are delocalized onto the C double bond O. So here inductive effect slightly dominates. So that is the reason why the decrease in the vibrational frequency. Whereas in amides, conjugation dominates. So that is why in amides we find the vibrational frequency at very less, that is at 1650 centimeter inverse. So out of all these acid chlorides, anhydrides, esters, amides will show lesser vibrational frequency. Then the other factor also we can add to this, that is the bond angles or the ring strain. So here we can see again the C double bond O frequencies. Here it is 1715, almost same here in cyclohexanone and this one. Whereas in cyclopentanone it is 1745. Then when we move on to cyclobutanone, it is 1780. Cyclopropanone is showing higher carbonyl frequency, that is 1815. So in this cyclopropanone, ring strain is found. So because of this ring strain, the vibrational frequency moves towards the higher wave number. So higher vibrational frequencies are seen when the molecules are highly strained. So we have completed the factors affecting the vibrational frequencies. Now we'll see the instrumentation part, how the spectra is being recorded and what are different parts of the IR spectrophotometer. So the main parts of IR spectrophotometer are IR radiation sources, we have monochromators, sample cells and sampling of substances, and detectors. So this is the block diagram of various parts of IR spectrometer. So this is the glowing wire or the IR source. This is actually double beam grating IR spectrophotometer. So reference cell, sample cell, we have mirrors and rotating segmented mirror here, monochromator, detector, and then the recorder. And you can see the IR absorption frequencies in this recorder. So now we'll deal with each one of the components here. First, IR radiation sources. So what are the various IR radiation sources that we have to use? And all the IR radiation sources, they should have high intense, because when the radiation is intense, then only it will be very easy to detect also. And the radiations should be steady. That means they should be uniform, extended over the desired wavelength. So whatever wavelength we need, so that particular wavelength has to be focused onto the sample. The various sources of IR are incandescent lamp, Nernst glower, globar source, mercury arc. Now what are these sources are? So Nernst glower, it is nothing but made up of rare earth oxides. So those are nothing but the oxides which are of zirconium, yttrium, thorium. And when these oxides are heated up to 1500 degrees centigrade, then they will produce the IR radiations. And the radiations are in the range 1 to 50 micrometers. That means they fall in mid to far IR. So this is the range where we can detect the various functional groups. Then globar. Globar, if we take as a radiation source, globar is the silicon carbide rod, which is heated at around again 1500 kelvins. Same range we observe 1 to 50 micrometers. Then we can use tungsten filament at 1100 Kelvin, where we can get only near IR radiations from that. Then mercury arc lamp by taking mercury plasma 50 to 300 micrometers, that is which are falling in far IR, can be obtained. So these are the various radiation sources that we can use for IR spectrometer, that is Nernst blower, globar, tungsten filament or mercury arc lamp. The second is monochromators. So the main use of monochromators is to select a particular wavelength of light. So it is used as dispersive element, and it is constructed of various metal halide salts are used. For example, sodium chloride is mainly used. So here you can see the prism where the sample is loaded. This is, and we can see that only a particular wavelength of the light is being coming out. Then we can also, instead of prisms, we can also use gratings. So gratings are nothing but rulings which are made on some materials such as glass, quartz or alkyl halides. Depending upon the instrument, we have different gratings. So what these gratings do is, so when the IR incident beam falls on these are the gratings. Okay. So when the IR beam is falling, or when it is incident onto these gratings, it will give different wavelengths of light. So these wavelengths of light are very important for IR study. Then how to prepare a sample or sample cell and sampling of substance. So the samples what we can take here in IR is, we can take samples which are in gaseous, liquids or solid state also. So the materials containing sample must be transparent to the IR radiations. And the salts generally we use are sodium chloride and potassium bromide. So these samples, we can take them in the form of pellets. We can convert that powder form, whatever is there, in the form of pellets, or we can directly take the liquid form of the sample also. So how we do this is sample handling. So if solid is present, how we can convert that solids into sample for the spectrophotometer. So we have 4 different types: solids run in solution, mull technique, pressed pellet technique, and solid film. So first, solid run in solution. So it is nothing but the solid whatever we are taking as a sample, we have to dissolve it in non-aqueous solvent and then place that drop of that solvent onto a metal disc, and that metal disc should be a alkali metal disc. So when what we have to do is take that solid sample, dissolve it in solvent, non-aqueous solvent, and then place that sample, just a drop is required, on the alkali metal disc, and just leave it for some time. The solvent will get evaporated. Then that film is taken and it is mounted on a spectrometer. So the solvents what we generally use for this solid run is acetone, cyclohexane, and chloroform. So all these can be evaporated very easily. Then mull technique. In mull technique, the powdered sample is taken and we have to add some nujol. Nujol is acting as mulling agent. So nujol is nothing but paraffin oil, where it is chemically inert. So we have to add this oil to this sample, powdered sample, and then make into a thick paste. That is nothing but mull. So a paste is made, and then that transfer the mold to the mold plates, and the plates are squeezed together to adjust the thickness. So two plates we have to take, that is we will be having two plates where this mold paste has to be kept between the two plates. So when you press those two plates, it will give rise to a very thin, that is the thickness will be very less, and that thickness we can adjust it, and it is ready to use for the study. Then pressed pellet technique. So in pressed pellet technique, the sample is mixed with KBr. It is mixed with around 100 times the weight of KBr, that is potassium bromide, in a vibrating mill, and then it is pressed. So here you can see the sample is placed, and then it is first mixed with the potassium bromide, and then it is pressed using a piston. So when you press it under high pressure, it will give rise to a pellets. So those pellets will be around 1 to 2 millimeters thick and 1 centimeter in diameter. So this is the thickness, that is 1 to 2 millimeters thick and 1 to 2 centimeter in diameter pellets. We can convert that sample into pellets. Then solid films. The solid films is nothing but, again, the solid is dissolved in volatile solvents, and this solution is poured on a rock salt plate. It is made up of sodium chloride or potassium bromide. And the solvent is evaporated just by gentle heating. So that is nothing but solid film you will get, which we can use it. Then sampling of liquids. So the liquid sample, whatever we have, we can just sandwich between two alkali halide plates. These are two alkali halide plates which are of sodium chloride or potassium bromide or calcium fluoride. So here in the figure you can see sodium chloride plate, and this is another sodium chloride plate, and in between we have to place the liquid sample. The sample thickness is just 0.01 to 0.05 mm. Then gases. If the sample is in the form of gases, it is just introduced into the glass cell, which is made up of sodium chloride. So generally, few organic compounds can be examined as gases. Example 1,4 dioxane. So if we have gases, we can directly fill into the cuvette, which is made up of sodium chloride. Then we have detectors. So detectors, we can use thermal detectors, pyroelectric detectors, or photoconducting detectors. So photoconducting detectors are very sensitive. So these are some of the examples of detectors. Thermocouple, we can use bolometer, Gaussian, pyroelectric, or photoconductive. So generally we'll be using photoconductive detectors, which are fast and sensitive. Then dispersive IR instrument. So this was introduced in 1940. So this is the IR instrument which is being used now. So the highly evolved spectrometer is Fourier transform IR instrument, that is FTIR. So why this is very important is, with FTIR we can get a that is the spectra, highly resoluted IR spectra we can get from FTIR. So what FTIR does is, it collects all the wavelengths simultaneously and at once. So it works based on the Michelson interferometer, which is having beam splitter, fixed mirror, movable mirror. So these are the other components which are present in the FTIR. So we'll look at the block diagram. So this is FTIR instrumentation, the light source. So from the light source, the light is falling on the mirror. That is, it falls on the beam splitter, where the light source is first broken into two beams. That is, it is separated into two beams. We will be having two mirrors. One will be fixed, the other one is movable mirror. So there are two mirrors. So the light which is coming from this mirror, when it falls on beam splitter, the beam is splitted. So one beam will go and fall on the movable mirror. The other beam will incident on this fixed mirror. Then what happens? Again, these beams, the light will be reflected back. They will again fall on the beam splitter. So this, when it falls on the beam splitter, these two waves, when it is coming from movable mirror and fixed mirror, when they are falling now on the beam mirror or beam splitter, one wave will move towards the sample. The other wave, again, it goes back to the light source. So the waves which are coming from these two mirrors, they may be coherent or they may be, we have two types, that is coherent and one is destructive coherent. So when it falls on the mirror and then when it is made to incident onto the sample will absorb some of the radiations and the other radiations will be transmitted out. So these transmitted out radiations, when they fall on the detector, the signal is detected and the detector will be connected to a recorder where the spectra is being recorded. So this is the block diagram of FTIR instrumentation. Now we will see what is interferogram. As we have said that FTIR works under the principle of Michael interferometer or interferogram. So interferogram is nothing but this is the right side here. You can see this is how the interferogram appears. The interference pattern, it can displays all the interference pattern and contains all of the spectral information. So actually the spectrum what we will get will be in this form. But in FTIR, this spectra is being converted into a function of frequency. So Fourier transform, FT stands for Fourier transform. So what it does is it converts the time domain spectra to the frequency domain spectra. So this is the spectra which is because of all the wavelengths which are undergoing absorption and then transmitted out radiations by the sample. But this is a very complex one, so we need to convert this into a frequency domain spectrum. So for that we use this Fourier transform. So this spectra is converted in this type, which is frequency domain. So here you can see it is all the absorption bands are very clear and we can easily identify what is the structure of the compound. So that is the main use of FTIR, where the time domain spectrum is being converted into a frequency domain spectrum. So now we'll recall all the points now, what we have studied till now. So IR spectroscopy, it is mainly used, the radiations used are IR radiations. When they are radiated onto the sample, the IR radiations passing onto the sample, some of the light will be transmitted out. So this transmitted light can also be helpful for studying the IR radiations. So IR radiations, when the frequencies of IR radiation matches the frequency of the vibrations of the molecules, the amplitude will increase. So because of that increase in amplitude of the vibration, the spectra is recorded. So these are the different types of molecular vibrations we have seen in our last class, stretching and bending modes. So how the spectra looks like. So spectra can be recorded. So for this absorption, so where there is no transmittance, so after coming out, the sample shows some transmittance, so there is dip in the transmissions. Okay, so that means there is no transmittance at all at particular places. So that is why the spectra looks in this inverted form. Then I have in Fourier transform IR spectrometer. So that is nothing but, as I said, there's a light source or the radiation source, which is nudged lobar. Then beam splitter, two mirrors, one is moving, the other is static mirror, sample, and then photodetector. So the nudged lower you can use as a IR radiation source. Then the rays which are falling onto the beam splitter first. So the beam is splitted into two parts. One is moving towards moving mirror, the other is moving towards static, and then it is again reflected back with this reverse arrow marks you can see. So when it is reflected, one beam again going back to the radiation source, the other passing through the sample, then transmitted out, detected, and then we'll get the interferogram. So here, as I said, when the two waves are coming back, they are in coherent, that is constructive coherent. So when constructive coherent, the transmittance is high. So it starts from the higher side. But what happens is when we move this, one of the mirror is movable mirror. Suppose if we move the mirror in this way, so what is happening, you can see the two waves are not in phase now. That means this term we call it as destructive coherence. So when destructive interference is taking place, the transmittance decreases. So this way, when the mirror is moving from A to B, so again we are getting constructive interference, that is transmittance will be more, then the transmittance again decreases. So this way we will get the spectra will be recorded. Now the light, whatever the radiation source we are taking, we will be having different wavelengths of light in it. So these wavelengths, different wavelengths of light or the wave, it will show this type of spectra, which is in, then it is converted into frequency domain spectra. Now we'll see how the spectra will be recorded. So sample measure, first we have to do the background or reference measurement, then sample measurement, then after that superimpose the two spectra. So background or reference measurement should be there. So first thing is we have to prepare the samples. So what are the different types of preparation of the samples? We can have solids, liquids, gases, or powders. So when we have gas or liquid as a sample, we can directly take in a cuvette made of sodium chloride. So transmitter light falls on the detector and then spectra is recorded, or you can take in the form of a pellets which are transparent to the IR radiations, or else we can use ATR crystals also, where the sample can be loaded on that. ATR stands for attenuated total reflectance, on which the sample is placed and then the IR source is irradiated onto the sample. So when the light falls on the sample, it is getting absorbed, little bit of the absorption is taking place and the remaining will get reflected back. And this reflected light will be recorded as the spectra. So instead of taking ATR, we also have multi-reflection ATR crystals. So where we can see the internal reflections, multi-internal reflections, not only one reflections, within the molecule internal reflections takes place. So what is the main use of using this multiple reflection is you will get a very good resolution spectra. And the sample, the other type is we can take powder form also. So these are pressed and they are being converted into pellets. Okay, so these pellets can be used as the sample where IR radiation is falling, and then we can detect the, we can record the spectra. Now we'll see how taking an example of Teflon, which is polytetrafluoroethylene, which is chemically resistant, and how to record the spectra of this. So first we have to clean that using deionized water, and then with using organic solvents, just clean the sample and then first do the background interferogram. So this background interferogram spectrum, it will be in this way. So this is nothing but because of the moisture and the carbon dioxide which is present in the machine. Now take the sample, load it on the ATR and then record the spectrum. So again the raw sample spectrum will give rise to this spectra, and this part is excess when we look at with that of the background spectrum. Background spectrum do not have these peaks. So these bands and this spectra, when you superimpose and cancel all the other, will left over with only the bands which are due to the sample. So this is how clean and clear IR spectra is being obtained. So we do not have these background spectra, which is due to the moisture and carbon dioxide present in the machine. So this is how IR spectra is being recorded. So hope you have understood what is what are the applications of applications we'll see in the next class, applications of IR spectrum. So in this class we have covered the various effects, that is the factors which are affecting the vibrational frequencies, and then the instrumentation part. So the application part, we are left with the application part that we'll see in our next class. So thank you. Hope you have understood till here. So thank you for watching.